Welcome to my video lecture based on utilization of electric power. Paper code EP702. Today my topic is laws of illumination engineering. In my previous lecture I have introduced about illumination and what is the basic difference between light and illumination, what are the basic definitions related to illumination. That part I have discussed in my last lecture. In this lecture, we will mainly highlight about the basic two laws of illumination engineering and related some numerical problem we will solve in this lecture. Myself, Rumul Banerjee, Assistant Professor of Electrical Engineering Department, Dr. Sudhir Chandrasekhar Institute of Technology and Force Complex. Previously, it was known as Dr. Sudhir Chandrasekhar Degree Engineering College. This institute is under various group. So let's start with laws of illumination engineering. Laws. Law means some rules or some basic principles which we need to follow in case of illumination. So the basic laws of illuminations are mainly two types. One, the law of inverse square, and second one, Lambert's-Cosine law. So first we will discuss about law of inverse square. So what is the law of inverse square? If a source of light which emits light equally in all directions be placed at the center of a hollow sphere, the light will fall uniformly on the inner space of the sphere. That is to say, which square millimeter of surface will receive the same amount of light. If the sphere be replaced by one of the larger radius, the same total amount of light is spread over a larger area proportional to the square of the radius. The amount which falls upon any square millimeter of such a surface, therefore, diminish as radius increases and will inversely proportional to the square of the distance. So here, basically we are considering a source of light which emits equally in all directions to be placed at the center of a hollow sphere. Okay, and the light will fall uniformly on the inner surface of the sphere, and each square millimeter of the surface will receive the same amount of light. That means we are considering that a source of light is emitting equally in all directions at a place at the center of a hollow sphere, and the light is falling uniformly on the inner surface of the sphere, and each square millimeter of the surface will receive the same amount of light. And next we have to consider, if the sphere is replaced by one of a larger radius, the same total amount of light is spread over the larger area proportional to the square of the radius. Now we are considering that whatever amount of radius sphere is there previously, now we are replacing the same amount of light for a larger sphere, and now same amount of light will spread for the large sphere. That means for each square millimeter, the same amount of light will be spreaded for larger area. So the amount which falls upon any square millimeter of such a surface will therefore diminish as the radius increases and will inversely proportional to the square of the distance. That means when the radius is increasing, the amount of light will be diminishes. That means the light will be spread over the larger area. That means it will reduce. Previously, whatever amount of illumination is created by the same amount of light, now it will illuminate lesser and will be inversely proportional to the square of the distance. Whatever amount of distance is need to cover, it is inversely proportional to the square of the distance. That means, if we increasing the distance, the light emission will be proportional to its inverse of distance squared. Okay. So, this is the source of light here. S. This is the source of light. Okay. And it is spread over this distance. This distance is R1 and this one is R2. For R1 distance, the light spreaded for a small area, and for R2 distance, light has to emit for larger area. Okay. So let's see. A similar relation holds if we have to deal with a beam of light in form of a cone or pyramid. The same situation will happen as per the figure. If we consider parallel surfaces which cut the pyramid at different distances from the source, the area of the surfaces are proportional to the square of the distance. Same thing. The area of the distance is proportional to the square of this distance, and therefore the amount of light which falls on one unit of the area of these surfaces is inversely proportional to the square of the distance. This relationship is referred to as law of inverse square. That means the law of inverse square is told to us in two ways. First one, when light is emitted on a sphere, and secondly, when light is emitted for a pyramid or cone. In both cases, we can see that the light emission will be proportional to inversely proportional with its distance square. So, this relationship is basically referred to as law of square inverse squares. Okay. Our law of inverse square, now we will illustrate it by mathematical calculation. So, for mathematical calculation, we can see, let us consider a surface area A1 and surface area A2 at a distance of R1 and R2 respectively from the point source of S of luminous intensity. So, this is the source and this is the square area of A1 and A2 where distance is R1 and second one distance is R2. And the luminous intensity is I and normal to the rays as shown in figure. Now let the solid angle subtended to be omega star radian. The solid angle is omega star radian. Okay. Luminous flux radiated per stadian is I, and total luminous flux radiated definitely it will be I into omega. The solid angle subtended, that is omega, so the total luminous flux radiated will be I into omega. Now illumination on the surface area A1, it will be I omega by A1. This one, the illumination for this surface, it will be I omega by A1. Okay. And similarly, the illumination on the surface area A1, it will be I omega by A1. Now, if our A1 is omega into R1 square, So it will be I divided by omega, I omega divided by omega r1 square. So I omega and omega cut out and it becomes I by r1 square. Okay. So similar calculation we can do it for A2 cross sectional area. Here it will be I omega by A2 and where A2 will be omega into R2 square. So ultimately it will be I by R2 square and this one I by R1 square. Okay. Hence, illumination of a surface is inversely proportional to the square of the distance. That means whatever we are getting, that is illumination of the surface area is inversely proportional with distance square. Inversely proportional with the distance square. Okay. And the light source, provided that distance between the surface and the source is sufficiently large so that the source can be regarded as a point source. Now we will come to the second law of illumination, that is Lambert's cosine law. In this law, we can say that very often the illuminated surface is not normal to the direction of light as AC in figure 7.6b. This one. Okay. This is the figure. But is inclined at AB. It is inclined at AB. Okay. The area over which the light is spread is then increased in the ratio of AB by AC. This is AB and this one AC. That is 1 by cos theta. This is the angle theta. So it will be 1 by cos theta. And illumination decreases in the ratio of cos theta by 1. So the expression of illumination becomes E equals to I cos theta divided by R square. Definitely R is the distance. Okay. So we know from previous law it is inversely proportional with distance square. So ultimately it becomes I cos theta by R square. So according to this law, the illumination at any point on the surface is proportional to the cosine of the angle between the normal at that point and the direction of luminous flux. Okay. So this is the second law of Lambert cosine law. Okay. Now we will discuss some numerical problem related to illumination, and definitely these numerical problems will be based on previous lecture where I have discussed about MSCP like that. Okay. So definitely you just follow my previous lecture for understanding this concept of MSCP. Now we will see some numerical problems related to this. So, our first problem is the flux emitted by a lamp in all directions is 1000 lumens. Calculate its MSCP. So, total luminous flux emitted is F. It is 1000 lumens. Now MSCP will be definitely the total luminous flux emitted divided by 4 pi. So here our total luminous flux emitted is 1000 lumens. So 1000 divided by 4 pi, that is 80 is the MSCP. Okay. Next problem. State the laws of illumination that I have already discussed. Two laws of illuminations. A 250 volts lamp has a total flux of 1500 lumens and takes a current of 0.4 ampere. Calculate 1. Lumen at per watt. Second, MSCP per watt. That means in this problem, we have to calculate the lumens per watt and MSCP per watt. So, first we have to calculate what is the wattage of the lamp. Definitely it is normal power formula, that is V into I. Here the V value is given, that is 250 volt, and I value is also given, the value of current, that is 0.4. So the total wattage of the lamp is 100 watts. Now, mean spherical candle lamp of power, that is MSCP equals to F by 4 pi. This is the formula, F by 4 pi. So here the value of F, that is given 1500 lumens. So it will be 1500 divided by 4 pi, that is 120 is the MSCP for this mean spherical candle. Now we have to calculate the lumens per watt. So the formula of lumens per watt is output of the lamp in lumens divided by the wattage of the lamp in watts. So output of the lamp in lumens in 1500 and wattage we have calculated 100. So the lumen per watt is 15. And second answer, that is MSCP per watt, definitely it will be MSCP of the lamp divided by the wattage of the lamp. So it will be 120 divided by 100, that is 1.2. So that means from this whole problem we have calculated the lumen per watt and MSCP per watt. Third problem. A 0.4 meter diameter diffusing sphere of opal glass, 20% absorption, encloses an incandescent lamp with a luminous flux of 4850 lumens. Calculate the average lumens of the sphere. Solution. Flux emitted by the globe, definitely it will be F, that is 0.8 into 4850. So where the total flux emitted by the globe is 3880 lumens. Now definitely the surface area of the globe will be 4 pi r square because it is a sphere and sphere area is 4 pi r square. So it will be 4 pi into 0.2, that is 0.16 pi. So average lumens of the sphere is flux emitted divided by the surface area. So it will be F divided by the surface area, that is 4 pi r square. So it will be 7720 lumens per meter square. Now example 4, that is filament lamp of 200 watt is suspended at a height of 5 meters above working plane and gives uniform illumination over an area of 4 meter diameter. Assuming efficiency of reflector as 50%, determine the illumination on the working plane. Efficiency of the lamp is 0.89 watt per CP. Okay. So, candle power of the lamp, that is CP, equals to wattage of the lamp divided by efficiency of lamp in watt divided by CP, that is 200 divided by 0.89, that is 224.72. Now, lumens output of lamp. Now we have to calculate the lumens output of lamp, that is pi C. So it will be 4 pi into Cp we have already calculated, that is 224.72. So it will be 2823.9 lumens. Now flux emitted per reflector. So it will be reflector efficiency into total output lumens. So it is ultimately 1411.95 lumens. And the area of working plane A equals to 4 d square by pi d square by 4. So it will be 4 pi meter square. Now illumination on working plane is basically lumens output divided by working plane area A. So it will be 1411.95 divided by 4 pi square, that is 112.36 lumens per meter square. So here I have discussed only 4 problems. There are various numerical problems related to illuminations, and definitely you can follow any books of utilization of electric power for understanding these numerical problems. And I will prefer that if you practice different problems related to illumination, then it will be easier for you to understand the concept of illumination. Because illumination is a vast concept. A small source of light can illuminate a larger area. That concept is based on the illumination, and how these things can be possible, that can be done through various numerical analysis. So definitely it is very important chapter, and students who are working in the area of light, or definitely different stadium lighting, or for any building lighting, street lighting, these total areas are different, and illumination for different areas are different. So definitely the calculations for different area will be separated. So for understanding this concept, you have to solve different numerical problems related to illumination. So definitely I will tell you that practice different problems related to illumination engineering to understand the concept of illumination. So thank you all for listening my lecture.